Hello, everybody. I'm extremely happy to introduce our speaker today. He's Yang Hui He. I didn't pronounce it well, but
no, it's good.
And you can see all his affiliations from his screen. And the title is also there, Universes of Big Data. But I also like the subtitle. This is Machine Learning Mathematical Structures. And at the end of his abstract, he said he would explain to us a bit of how can artificial intelligence help us with mathematics. So please, Yang Hui.
Thank you very much. Thank you very much, Alicia, for the kind invitation. So it's a pleasure to be speaking at GEOTOP. Sounds, I love this name, GEOTOP. I'm not sure what the A stands for. Probably Alliance. I don't know.
Applied.
Applied. Okay, I see. And so I've changed my title slightly because the original title was Universes as Big Data, from geometry to string theory to machine learning. But I think the majority of the audience here are applied and pure mathematicians. So I would talk a little bit more. I would start a little bit about how this problem arose, but I will focus more on about machine learning of various mathematical structures and experiments that I've been doing over the last 5 years or so. So let me just give this is of course this is not a string theory audience, but I'm just going to give you a 2-slide summary of how I got into this stuff, because my background is sort of the intersection between string theory and algebraic geometry. But so how did this kind of problems originally arose? So as people probably know from various public sources, string theory is a unified theory of everything, in the sense that it is a theory of quantum gravity that try to unify general relativity with quantum field theory. The downside to this, or upside, however you want to take it, is that this is a theory that exists in 10 dimensions. This is a 10-dimensional space-time theory, of quantum gravity. But we don't live in 10 dimensions, but we live pretty clearly, we live in 4 dimensions. And so we're missing 6 extra dimensions. So from the very early days of string theory, namely in the mid-1980s, people like Candelas, Della Ossa, and Witten, and Strominger and friends realized that one particular solution, and it's since become the canonical solution of these 6 extra dimensions, is some kind of a Ricci flat Kähler manifold. So that was the basic background of this. But whatever it is, the point about, as far as this community is concerned, the community of pure and applied geometers is concerned, is that the geometry, or the algebraic, differential, and the geometry of the topology, in various combinations of these words, of these extra dimensions should determine the physics of our world. So that's the basic upshot about string theory. So this is the last time I will mention string theory. So this is why the string theory community has become such good friends with the mathematics community. It's because you can translate the physics of our world, whether it's general relativity or particle content of a standard model or whatever, or fermions or whatever. You can translate this as a dictionary. You can take this to the very precise problem in algebraic and differential geometry of these extra dimensions. So that's all very nice. So by looking for whether the universe looks like our universe, you just look for certain geometrical properties of this for example, the 6-dimensional manifold. But there's a big problem. So everything comes with a price. It is a problem that solves the theory of everything. But the biggest theoretical challenge of this whole paradigm of string theory, and is particularly of particular interest to mathematicians, is what's so-called the vacuum degeneracy problem. In the sense that there are simply too many possible solutions for this X. And I'm talking about a lot. We're talking about 10 to the 10 to the something number of solutions. So for example, as I mentioned earlier in the mid-80s, when people realized that this 6 manifold can be taken to be a Clavial complex threefold, this Kähler-Ricci flat threefold, even in this subclass of solutions, there are too many possibilities. And the basic reason for this is that the topology and combinatorics tend to grow exponentially. So for example, if you ask, how many Clavial 1 folds are there? Well, that's Ricci flat complex curves. Well, there's essentially only one, the torus, T2. And if you were to ask, well, how many of them in dimension 2, complex dimension 2? Well, there's the 4 torus, and there's the K3 surface. So there's 2 of them. So in dimension 3, you imagine maybe there are not too many. But in dimension 3, there's already, physicists and mathematicians have worked in the past few decades, and we've literally written down over 10 to the 10 number of them. It's not crazy. 10 to the 10 is about 1 terabyte of data on your laptop, and you can just really list them out. So just to give you an idea why this is the case. So let's look at reflexive polygons. So while we're looking at this, so reflexive polygons are lattice polygons which have a single interior point, such that all of the bounding surface, the bounding facets, so here just the edges, is distance 1 from the single interior point. So reflexive polygons have been classified by the Italian school of algebraic geometry back in the 1890s. So of course by classification I mean these objects up to SL2Z. Right? And this is a finite set and exactly 16 of them. And the point is that there's a beautiful theorem of Borisov and Batyrev in the late 90s, which says if you take any of these objects, these combinatorial objects, you write down the compact toric variety from this data, then you take the anti-canonical divisor within this toric variety, it will be Clavial. So this theorem guarantees a very efficient way to create Clavial manifolds. So here, these are toric polygons. These are reflexive polygons. So the toric varieties you can write for them are 2-dimensional complex varieties. They're Fano varieties. And you take the anti-canonical divisor in them, you get a Clavial hypersurface. So this, in this case, will be a hypersurface of dimension 1. So there will be elliptic curves. So there are 16 very distinguished elliptic curves that you can write. So that's nice. And then what about the next dimension? How many how many reflexive polyhedron are there? Polyhedra are there? And that problem is, these are polyhedra with lattice vertices, such that there's a single interior lattice point you can take to the origin, and such that all of the bounding faces is distance 1 from this. This classification problem was already unknown in the mathematics community from like the 1890s. It had to wait 100 years before physicists tackled this problem. And this was done by Kreutzer and Schaka in their very impressive work in the late 90s. And they just literally enumerated them by brute computer force. And they found 4,319 of these objects. So polyhedra with integer vertices with a single interior point, and such that every face is distance 1, up to SL3Z. So they found this number. So these would automatically give you Clavial 2 folds by the theorem of Batyrev and Borisov. But still not good enough. What about the next one, the Clavial 3 folds? Because these are the 6-dimensional manifolds. And so they actually, Kreutzer and Schaka actually went and, brute force using the Pentium chip in the late 90s. And they found this remarkable number. There are 473 million of this. So each one of these, so they're reflexive 4 polytopes in dimension 4, and you can construct a 4-dimensional toric variety, and then the hypersurface in those will be Clavial. So suddenly it grew, this zoo, even in the Clavial case, grew to something like 500 million, by the late 90s, which is quite impressive work. We have no idea what the next number is. It's at least 185 billion by some recent work estimates of Schaka. So that's kind of interesting. So this is just, I'm just giving you this very concrete example in combinatorial geometry as just to give you an idea the exponential growth rate of this landscape of possible geometries which are relevant to physics. So suddenly we're dealing with something like billions and billions. So And that's just searching for it. So each one of them could create a potential universe. And we're looking for the physics of this. So you got to compute topological invariants, various fancy stuff on these manifolds to just get an idea what the physics is. So maybe you say, well, maybe a billion of these I can scan case by case, but it's still that computationally it is very, very difficult because computing, cohomology of bundles over this of a billion varieties is not so easy, even by the best computing resources. So here's a shameless self-advertisement. So this book just came out last year. Very proud of it. If you want to read a bit about the history of why these geometries came about in the physics and its dialogue with mathematicians, you can buy this book, and I can get royalties. Well, not very much. So, but the point is that you can compute the idea is there now. But it is now becoming a pure computational problem, right? As I said, particles in interactions are cohomology theory on these manifolds. If you want to compute masses of particles, you need to compute certain properties of the metric. If you want to compute what's called the Yukawa couplings that give the masses, so there's certain triple intersection numbers you need to compute for these varieties. So this is all very nice, and you can take various approaches to this.Maybe our universe is what it is because of certain anthropic principle, or maybe there is a selection principle of why our universe is very, very special that comes from the space of geometries. Or you can say, well, maybe we're just one part of a multiverse. And these are certain physics motivated problems. But what got me really thinking into this problem was, well, here's a wild question. If you think about a typical problem in string theory, or indeed, what is a typical problem in algebraic geometry? Well, you're given some kind of input tensor, or input integer, or tensor, or real tensor, and you're trying to crunch out some kind of integer output, right? So, for example, I give you an algebraic variety in some multiproj. I can keep track of the multi-degrees of the polynomials that define this algebraic variety. And at the end of the day, I just want to crunch out, what's a Hodge number or a Betti number or some topological invariant. And in principle, we know how to do it. And I'm very grateful for, over the years, people like Mike Stillman and Hao Shank and my friend Heather Harrington, they've been teaching me the proper way to do this computation. You chase sequences until you're blue in the face, and then you crunch out this particular invariant, which is fine. And things like Macaulay 2 and Sage now can do such computation. But as you well know, the bottleneck in computational algebraic geometry is the Grobner basis. A Grobner basis is a double exponential running algorithm. So it's a very, very difficult thing. And if you have to dealing with billions or 10 to the 10 to something of 10 to the 10 to the something number of the varieties for which you have to compute such invariants in order to get the physics, it becomes exponentially difficult. It'll take longer than the age of the universe to search for the universe which is like ours. So this is a very paradoxical problem. So I was thinking, well, this kind of a problem in algebraic geometry, but isn't this exactly the kind of problem that's perfect for machine learning? Because that's what machine learning is. You take an integer tensor input and you spit out some integer output, right? This is like the perfect kind of problem. So that's what got me thinking in 2017 was at the time I was thinking about it, can you deep learn the landscape of string theory? But then what motivated me to thinking, well, can we actually machine learn the landscape of algebraic geometry? So let me just give you, well, I'm very much an amateur in machine learning. So I just want to share with you my inexpertise with machine learning in 1 minute, just to set the background what machine learning actually is to this community of I think I'm assuming the vast number of the audience here are algebraic geometers and topologists. So I'll just give a 1 minute overview of what supervised machine learning actually is. So the problem is like the analog. So So if I write these digits from 0 to 1, this is how I write it. How do you make the computer recognize this? So in other words, you want to take a bijection from this set to this set. Well, if you ask a mathematician, how would you do this? Well, he or she will say, well, maybe we find a clever Morse function. You detect the critical points of these numbers, or maybe compute persistent homology. Do your favorite thing. But these are highly inefficient ways of actually setting up this bijection. What does your phone do? Well, your phone doesn't do this problem. What your phone does is to go to the Nist Database. This is the National Institute of Standards. And this is a database that's actually been labeled by poor graduate students since 1960s. So they literally take hundreds of thousands of handwritten digits of this way, and then some poor teams of graduate students, some large parallel clusters of graduate students have actually labeled this in one by one since the 1960s. So Google has access to this database, and then it will start doing machine learning algorithm on this set of association rules. Just to be precise, so the association rules is as follows. You take typically a 28 by 28 by RGB data. So this is a tensor. So these are 28 by 28 pixels. And the RGB data here is even easier because I'm just using grayscale. So this is a 28 by 28 matrix. And the entry of each entry is then some integer between 0 and 1 to tell you how gray it is. So this is good enough to specify all of these numbers. So perfect. This is an integer. This is a tensor input, and then I want to compute. Well, I want to be able to associate the numbers as they are. So I want to somehow recognize this integer with this tensor as the number 3. So what you do is you feed it to some neural network. So a single neuron, let's just go way back. People were thinking about it in 1957. I was very surprised to find. So a single neuron is called a perceptron, and all that is that you want to imitate something of a neuron. So this comes with an activation function, and you have some weights and biases. And typically, such a function is a sigmoid or hyperbolic tangent function. So this is something that imitates a neuron, and then you give it some training data. So, in other words, what the poor graduate students have been labeling for 70 years, and then a particular known output, and then you minimize some cost function, typically some standard deviation. So your x's are your tensor input, and you want to find some weights and biases which minimize this particular cost function, and then you check against some set of validation data to see how well you've done. So, of course, what this is just nonlinear regression. This is just a single neuron in a neural network is just nonlinear regression by some function of such a type. The magic happens, and this is something that was realized in the mid-80s, is that what if you put a network of such activation together, and such a network is called the neural network. And so this is called the input layer, and then this is output layer, and there could be many, many hidden layers. And the more layers there are, the deeper your network. So somehow the connectivity of this neural network gives you emergence of complexity. So in other words, you feed in your tensors representing these integers, these handwritten digits, and you want connectivity to do the magic. So the point is, there are universal approximation theorems. So I won't bore you with the details, but these theorems, proven in the last 10, 20 years or so, is essentially the statement that given a sufficiently complicated network graph, you can approximate any function. So you can sort of imagine this happening. It's like saying, a Taylor series expansion can approximate any analytic function. And the idea here is a sufficiently complicated network of simple activation functions can approximate anything, even non-analytic functions. Even the theorem is even more more broad in the sense a ReLU function. So this is a function that looks like an activation function, if you just use an activation function, which is just a line and then a broken line, even this piecewise linear function, if every activation function is of this form, it is good enough to approximate almost any input or any output. So this is what's meant by the emergence of a complexity by connectivity. So you're basically looking at a universal approximator. So back to this idea. Well, then I was thinking, well, since there are such good theorems, is it possible that we can approximate any computation in our algebraic geometry? Well, it might be possible. I don't know. So let's try it. So here I've given. So I was, we as physicists and mathematicians, we are very lucky because everything for us is free. There are databases, as I mentioned, this reflexive polytope data, all of this data is freely online. And then, say, the NHS, where you have to pay to get their data. But this is just free, so you can just mine it. So here's a typical computation algebraic geometry. You take a variety. Here's a Clavial threefold defined by the complete intersection of 8 polynomials. So 1, 2, 3, 4, 5, 8. Embedded in products of projective space. So these are the multi-degrees in the multi-proj. The details are not important. And then you compute its H11, this Hodge number, and it turns out to be this number. It doesn't matter. And the proper way to do it, as I said, people like Mike Stillman and Hao Shang tell me how to do it. You get some embedding of the Euler sequence. You induce the non-exact sequence to homology, and you chase this diagram. A lot of this is implemented, of course, in Sage Math and in Macaulay too. And then at the end of the day, you just get some integer, right? But of course, computing this is doubly exponentially difficult. But nevertheless, there are databases where such association rules have been done. So, well, the question is then, you can represent such an input simply as an image. It doesn't matter, right? I mean, some neural network has no idea what it's doing. All it's doing is this association rule. This picture, which represents this variety, should be associated with the number 8 for its Hodge number. And so then we have exactly the kind of problems that is perfect for supervised machine learning. So by the way, what I've said a bit earlier is the paradigm of supervised machine learning, where you have a specific input and an association rule with an output. So basically, machine learning go into 2 big categories: supervised, like over there said, and unsupervised. Unsupervised machine learning is just where you get this data and you try to mine to see whether there's structure in it, like cluster analysis. So this is the 2 big paradigms of machine learning. But here, for our purpose of computing topological invariants of algebraic varieties, it's a perfectly adapted problem for supervised learning. So here, so then what you do, you take 5,000 of these picture associations, train a neural network, tune it a little bit, and then you validate your neural network, which has been, the weights and biases of all the activation functions have been sort of rigid after the training, and then you check on varieties it's never seen before, and varieties in the same database where we know the answer, which is how well it's doing. So to be honest, when I was doing this in 2017, I had no idea. I mean, I just had this hope, this prayer that maybe it'll do well. But surprisingly, it was doing extremely well very, very quickly. In a matter of seconds, it was getting up in the high 90s of precision, which was a bit unexpected. Well, I guess in retrospect, maybe it's because of the universal approximation theorem at work, but universal approximation theorem required very large and very deep neural networks. I was using something with 2 layers and 3 layers. So something about algebraic geometry, something inherent about algebraic geometry, there's structure in there which makes computation like this even possible. So that was kind of great, that this is doable. So it made me very happy. So since then, there've been, I won't bore you with the details. This has become an integral part of the string theorists' toolbox. we physicists, we like to, we're cheap, right? We get whatever, toolboxes we can get from anybody, and we try to beat on this problem of finding universes. So here is another toolbox. But this toolbox, to be fair, is a very mysterious one, because we can't actually interpret what is going on under the hood. I mean, I can tell you all of the activation functions and all of the various problems, but, what can you actually interpret? So, well, hopefully, now let me get into the sort of the heart of the problem. Why stop at string theory in geometry? How many problems in the mathematics can you throw at a generic neural network to make it recognize a pattern? So this is what got me into thinking, and this is sort of the main part of the talk that I want to focus on. I will tell you some experiments. So this is it's a fun talk in the sense that I will get into so many different random problems. So this is to keep people awake and not fall asleep. So you can fall asleep in every 2 minutes, and then I'll tell you some different problem that you can try. So before I can do this, I don't know, it got me thinking into some more foundational problems, right? So this neural network approach to mathematics, or indeed in general machine learning approach to mathematics, makes me think about something that's sort of in parallel. So how does one actually do mathematics? Well, one can think, well, maybe, this problem you can think about going back to Russell and Whitehead, in their Principia Mathematica, this entire program in axiomatizing mathematics, line by line. But we know that this program was killed by Gödel, Church, and Turing, because they've shown that there are unprovable statements within any order of logic. But this problem, this Gödel, Church, Turing's, death blow to the Russell-Whitehead program did not intimidate mathematicians from actually formally trying to prove mathematics. Because in the sense that, the practicing, I think Min Young Kim was the one who told me this, the practicing mathematician hardly ever worries about Gödel. Yeah, sure, there are undecidable problems, but, chances are the theorem that you'll have to prove, this month is not one of them, right, in that sense. So this, despite this, people have been pursuing this idea of automated theorem proving, which is exactly, line by line, axiom by axiom, statement by statement, logical symbol by logical symbol, trying to reconstruct all of mathematics. And this is a program that goes back to, again, 1950s. It's interestingly around about the same year as machine learning, but this has got nothing to do with machine learning. And then this has really become a huge program called the ATP program, which, I know nothing about this, but this, for a moment, let me call this bottom-up mathematics, right? You're really writing down mathematics as a linguistic model of symbols, and then you try to recreate proofs. And then the big proponents for this are people like Kevin Buzzard and Davenport, especially in their ICM address of 2018 of so-called computer-assisted proofs. So here's what they call it. They're using this program called Lean, where apparently you could write down axioms and you write down the statement, and Lean will start to construct intermediate steps for proofs. So Kevin Buzzard, who's a big proponent in this, are so optimistic about this that they foresee within 10 years, ATP program will prove every undergraduate level theorem. I've seen this. I've seen him giving talks like this. I was seriously impressed. Like, you could write down, I don't know, define a point, define a line, and then I want to reach Pythagoras. How do I do it? And you hit return. The computer will start searching its own strategies and start giving line by line. I mean, so far it's not very efficient, but it will give you absolutely correct intermediate steps from the definition of a line and the axioms of Euclid, and will get to you the proof of Pythagoras. And so there are people at Google DeepMind who think that computers have beat humans in chess in the 1990s. In Go in 2018, by extrapolation, it should beat humans in proving theorems by 2030. So we will see this within our lifetime. So within the next decade, we should see every theorem at the undergraduate level being proven automatically, and then hopefully it'll start generating new theorems. So this is one direction, which I want to call this bottom-up mathematics. What I'm saying here is something different. which is sort of the complementary direction, and I'm borrowing another physics word, which I'm going to call top-down mathematics. Because, mathematicians, we don't really do mathematics in this ATP kind of way, unless you're Russell and Whitehead. We don't write down axioms as symbols and try to go from there to, like, I don't know, some advanced theorem in algebraic geometry. There's a lot of intuition and experience and experimentation. Right, so I like to draw this analogy. It's like, what is the best neural network of the 19th century? Well, it's the brain of Gauss, for sure. That's a fantastic neural network. Gauss can look at this diagram and say, well, this is x over log x, and that's the prime number theorem. So in some sense, he wasn't constructing this from bottom up. He was looking at top down because Gauss had all other things available to him. He didn't have an available complex analysis, but he was able to predict without complex analysis that this plot is x over log x. And you had to wait until complex analysis to prove it. And similarly, you can think of BSD, the Birch-Swinnerton-Dyer conjecture started with just Birch and Swinnerton-Dyer plotting ranks and conductors of elliptic curves. In the 1960s, in the big ENIAC machine, whatever machine they were using, and just try to see patterns there. So the machine learning paradigm is really sort of the 21st century version of experimental mathematics of this type, but at a much more sophisticated level. So the conjunction of this top-down and bottom-up approach, I think, should be very, very fruitful in generating new mathematics. So in other words, let's be very precise. I give you matrices of this type, right? Or in fact, better, I'm going to give you association rules of this type, for example. Can you run a generic machine learning algorithm to extrapolate and conjecture a formula, just like Gauss was able to recognize this is x over log x? And another very interesting question is, by looking at sufficient a number of this, let's say 100,000 of such data, could you actually tell me which branch of mathematics is likely to come from? Is it combinatorics, algebraic geometry, number theory? I don't know. So this is a kind of experiment that I will tell you about shortly. So this is very different from the kind of data that's usually fed into machine learning. Machine learning is very good at noisy data. It's very good at trying to extrapolate because it's usually people like image recognition. There's some kind of noise, but here it's pure data, noiseless pure data in the sense of mathematical data. So this is why one of the reasons I wasn't expecting it to do so well with problems in mathematics, and yet it was. And let me try to at least speculate why it should be the case. So let me just summarize now in the sense that we want some kind of experimentation on pure mathematical data across various disciplines, which would then raise possible conjectures, and then this should be used in conjunction with this bottom-up ATP approach to mathematics. So let me tell you some experiments. So again, what is interesting is I'm going to use various standard machine learning tools, like forward feed neural networks or support vector machines. These things are all regressors and classifiers. And I'm going to take the standard 20/80 split. I'm going to look at 20% of the data that's available. Then I'm going to validate on the unseen 80%. It's very important that in machine learning to do this what's known as cross-validation, where your training data is distinct from your validation data. Because there's so many parameters. If you just validate on the stuff that you've seen before, you could be overfitting by quite a bit because there's so many parameters.
How do you
so let's try.
Yes. How do you choose the 20%? How do you choose which 20%?
Yeah, good, very good. So I would actually choose randomly 20%, and then I would do this several times, and then take the average of the precision reached. So one of the standard ways to do it is actually in the machine learning community, they do what's known as a fivefold cross-validation, which what they do is they divide the data into random 5 chunks. They train on randomly into 5 chunks, and they do 4 chunks. So they actually train on 80%, and then validate on the remaining 20. I'm just confident, mathematics, because mathematical data is so noiseless, it's good enough to just train on 20 and validate on 80. So I'm being like overconfident. And it kind of works. Don't know why. Yeah, that's a good question. So let's try a crazy question. So this is something very simple. And this is a problem that's originally recommended to me by Min-Young Kim, who is a very insightful number theorist. He says, well, we know we know what a Latin square is. This is a Sudoku. This is like an n by n square that's from 1 to n, and no repeats in any column or row. And we know the Cayley multiplication table of any finite group is a Sudoku, but not the other way around. Because a Sudoku has to obey further associativity rules in order to be the multiplication table of a finite group. So the first question asked me was, if I send you 100,000 groups, or not groups, but that you can do it, but that will become computation expensive. Can you recognize one that's actually a Cayley table? So we tried the first, 1,000 groups or so, but then you do permutation enhancement because these things are only defined in permutation. So you can easily generate 100 or 10 to the 5 to 10 to the 6 groups. Then you do exactly this trick. And very quickly, a neural network can do 0.9%, 95% accuracy with 90% confidence. So at this point, the first number I'm reporting here is the naive precision of correctness, and the second one is the chi-squared. So just as an extra confidence check. So that was pretty good that you could recognize this problem. Okay, so that was a warm-up. But now here's a much more interesting problem, and it's almost a proto-conjecture. Now, can you look at the space of Cayley tables and recognize that this is a Cayley table for finite simple group? So that's a highly non-trivial calculation. In principle, we know how to do it. You give me the Cayley table. For example, one way to do it, you give me the Cayley table. I will know the structure of the group. I will write down the character table of this group, which is already a non-trivial computation. Then from the structure of the character table, there are theorems which tell you whether it's simple or not. But so it's a non-trivial step. Just like sequence chasing in algebraic geometry. There's many hidden steps that you need to do. But then what we did is, we took these Cayley tables of the space of groups. I think we took the first, several hundred, and then mixed it all up. And then, and then you flatten these Cayley tables into a vector space of dimension n squared, and just plot this in this high dimensional space. But luckily, there's precisely something in machine learning which detects this kind of structure in high dimensions. You can't plot it anymore, and it's called a spot vector machine. What it specializes in is to try to find hypersurfaces which tend to separate. So
could I ask you?
Yes.
I'm sorry. Could I ask you a question?
Yes.
Just on whenever people give me, 95% accuracy or other things like that, I always wonder if you've looked at the actual errors. So have you examined the errors that you're getting there, and are there any way to classify or cluster those failures?
That's an extremely good question. This is in progress. We have the confusion table in each case, and then we're picking out the ones that is misclassified. But it's very difficult to pinpoint exactly why it's doing wrong. So there is an entire field of machine learning in this error detection of misclassification, and I am working with or have been working with card carrying machine learners to try to see how much information you can get. But I don't have anything to report just yet. Hopefully, at some point I can tell you why it's misclassifying those. You've hit on exactly the good point. Yeah.
Thank you.
Sure. But you do this plot, and the support vector machine is actually separating the simple groups from the finite non-simple groups. So it's just kind of crazy. There are no theorems of such a type. I don't even know how to even begin to approach a problem of such a type. Of course, just regarding the previous question, once you hit 100% accuracy all the time, and this is now beginning to emerge in the field, and I can give you some references later, you can actually conjecture. This is a precise conjecture, which you can then prove. So we have have begun to reach this level where very precise statements are reached. So this is very, very exciting. And there was a recent Google DeepMind paper on this. I will mention a bit later.
Can I bug you with one other question? Can I bug you with one other question?
Yeah, of course.
When you're using the support vector machines or other things as far as embedding into Rn, are you just taking naively the coordinates of the Cayley table, or are you looking to do it?
Yeah, literally just that. Yeah. So I mean, in this case, it's a bit of a cheat. It's not Rn; it's really Zn, or Zn, because it's just a list of integers. It's just flattened into a very long string. And I think it's because we take all of the Cayley tables together with random permutations of them, so they're all mixed up. And in addition, so with that kind of structure, so there's no particular bias to any choice of direction. So it's all mixed up. There's some complete linear map that mixes it all up, some permutation map that mixes it all up. And then that space we're looking at, and somehow there's this separating hypersurface that takes the simple from non-simples. And of course, this should be improved. We should take higher, and more and more groups, and then try to get a 100% accuracy. And then, I mean, I can tell you the equation of that hypersurface, or at least order by order. And I don't know why that should even exist. So this is kind of interesting. So it seems to be that these simple groups and non-simple groups are really separated, but they're separated in a very strange way.
Really fascinating. Thank you.
Yeah. So that was fun. By the way, this talk is totally fun because I'm not giving you any theorems, so I hold no responsibility. I'm just giving you experiments and what the results are. So there can be no mistakes in this talk. It's just reporting experimental observation. So let's try something else. So that was from group theory. Like, what would I try? I don't know, combinatorics. So we try something like this, and then this is some work with Yao. I was very surprised that Yao was interested in this. In fact, Yao is so much into machine learning now. He's founded a new institute in Beijing called BIMSA, dedicated to theoretical physics, applied mathematics, and machine learning. This huge, because Yao is Yao, he says, I need 1 billion to do this. And the government says, here's 1 billion, you can do this. This is a fantastic way to do mathematics. And then there's this giant campus just built to do theoretical physics, applied and pure mathematics, and machine learning. So that's why he was interested in this kind of problem. So here's a little more difficult. You see the accuracy level drops a little bit. We were just testing things like, can you look at graph properties? Can you detect its genus? Can you look at the existence of Hamilton or Euler cycles, or whether it's a planar graph, just looking at the adjacency matrix of the graph, plus all possible permutations. And this is tested within a database. So Wolfram has a database, I think, of around about 10,000 graphs, at least the 10,000 graphs that have names attached to them. And then you add in all possible, not all possible, but all random, you can add lots and lots of random permutation to this. You can easily get, 10 to the 6 to 10 to the 7 number of such features. And here, you can see that the performance is just dropping a little. It's not random, but it's dropping a little bit. So I learned from my machine learning friends is that a very difficult thing for machine learning to detect is whether two graphs are isomorphic. Even that's a very difficult problem. So detecting, permutation equivalence is a very difficult thing for the generic neural network, at least. But at least still, it is very encouraging that algebraic geometry, at least algebraic geometry over C, was responding so well to just very out-of-the-box machine learning algorithm. And I think the fundamental reason for that is that the core computations for algebraic geometry is finding kernels and co-kernels of matrices, right? So if you're doing some very complicated non-exact sequence, in some monomial basis, you are just chasing kernels and co-kernels of matrices. And finding kernels and co-kernels of matrices, that is something that a neural network can do very, very well. So in your in your feature detection, like image recognition problems, you are constantly doing this problem. And in fact, so sort of the prototypical problems in machine learning are precisely geared toward this kind of problems, finding kernels, finding null spaces of matrices. So this is nice. So we've gone through several fields. We've gone through theoretical physics. We've gone through algebraic geometry, representation theory, combinatorics, and then here's something that you would find entertaining, and that is there's got to be something that'll break it, right? There's got to be one class. If you were asking me what branch of mathematics will definitely not be machine learnable, well, supposedly, and I would guess probably the distribution of primes or any hard problems from analytic number theory. And so let's try it. Let's see if indeed this is the case, right? So let's take some data like this, right? I want to predict the next prime. And so there's no way. This is just, I couldn't find anything. And I don't think anybody's ever found anything. And that's fine, because if I can factorize integers in this way, then I'll be able to break every single bank efficiently, right? It doesn't even matter whether I'm just doing this stochastically. If I can just find the factors of an integer stochastically, I can just try that a few times, and then I can break your credit card. But luckily for you, this doesn't work. I'm trying, but it doesn't work. And so let's try. So okay, maybe you can say, well, maybe this is too much variation. This is a sequence prediction problem. And there are recurrence neural networks which does this sort of thing, but it's very, very difficult. But let's try a slightly easier one. Let's take a window, a sliding window along the odd integers. Right, so let's forget about the even ones. We can just, that's too trivial. Let's just, by this I mean, let's take the odd integers, starting from 3, and I'm going to label 1 if it's prime, 0 if it's not prime. So now I have just a sequence of an infinite binary string, and now I'm going to take a window, say 1000, and you can scale this window by x over log x if you wish, if you want to take prime number theorem, the distribution into account. And then I just want to predict what the next one immediately outside the window is. Is it a 1 or is it a 0? And if you do this, you don't get very good results. You get 70% accuracy in predicting the next number. It's not 0. There might be reasons why it's not 0. Maybe it's I don't know. It's I don't know why it's not. Oh, sorry, it's not 50%.
Quick question, what's your accuracy within class? As far as like, if the next one is a prime, what's your accuracy?
Oh, sorry, yeah, sorry. By 70%, I mean the percentage of the ones that have agreed. So the percentage is 1s and 0s together. So the percentage of correct predictions, whether it's a 1, where a 1 is supposed to be a 1 and a 0 is supposed to be a 0. Is that the question?
Maybe I'm misunderstanding. I apologize if I am. You were trying to predict in this next window, is there going to be a prime? Where is this prime going to be? So if the
sorry, no, sorry, I didn't explain. So my window is say like length of 1000. So of this ones and zeros is a binary vector, and I just want to predict whether the next one is a 1 or a 0.
Right, and so if the next one is a 1, then it's a prime.
It's a hit, yeah. If it's the next one is a 1 and my neural network predicts it's a 1, it's a hit. If the next one is not a prime and my neural network predicts that it's not a prime, it's also a hit.
Right. So I was wondering, what are your hits when the next one is a prime? So, for example, I could make a stupid one that just always says is not a prime, and I'll have some degree of accuracy based on.
Oh yeah, that's true. That's a good point. Yes. I don't. I should have included my. So that information would be contained in the confusion table.
Right.
Yeah. Yeah. I should. But I can tell you the chi-square of that confusion table is about 80%.
Okay. Thank you.
Okay. Yeah, I should have presented that. Oh, we can actually probably do this in real time. I mean, it's such, just a few lines code. Is just try it. Perhaps the more interesting one is the next one, which is Sonax challenge. So Sonax, Sonax of course is he's a real card-carrying analytic number theorist, and he thinks that if anybody can predict the Liouville lambda function over the integers, that would be truly spectacular. And of course, he made this statement years ago. So the Liouville lambda is just, I will scale it. I will scale it a bit. But this is essentially, if you I give you an integer, whether this integer has an even or an odd number of prime factors up to multiplicity. So that's the Liouville lambda. And apparently, card-carrying number theorists consider this a really, really, really difficult analytic function to understand. So much so that there have been not very much progress in trying to get a control of this function. So you can do the same thing, but it's fine. You take all of the integers, starting say even including 1 in this case, and then you label it 1 if it has an even number of prime factors up to multiplicity, or 0 if it doesn't. And now you have a binary classification of a binary vector, exactly the same kind of way that that would do say like in the Cayley tables or in algebraic geometry. You have this binary classification problem, and if this problem came from algebraic geometry, I would bet you money it will get over 90% very, very quickly. But in this problem, I tried everything on God's green earth. From deep neural networks, from convolutional networks, support mechanisms, try. Nothing ever broke 0.5. And that 0.5 is exactly as you said earlier, it's just randomly guessing. That because it's either 1 or 0, right? So you cannot. And then this chi-square is 0.001. I mean, in these experiments, meaning that my confusion matrix is essentially completely mixed up, and there's no prediction on this direction, which is kind of, I don't know. It's simultaneously disappointing that at least naive neural networks couldn't hit hard problems in analytic number theory, but it is also very reassuring that analytic number theory is the hardest one, because it goes with your intuition that Diophantine problems are indeed the hardest one to crack in some kind of computational way. So, and then we tried various things. So I won't bore you with the details of all the experiments, but then I started talking to card-carrying arithmetic geometers like Kyo-Hwan Lee and Tom Oliver, who said, well, fine, but maybe arithmetic geometry is better than hard arithmetic. If you don't muck around with just analytic properties of primes, let's try what arithmetic geometers would do, namely to try, to look at, the correct arithmetic properties of things like elliptic curves. And so there we tried various experiments with very, very simple classifiers again. And again, you see very happy numbers again. Okay. So let me just give you an example of what kind of experiments you want to do here. So instead of, I mean, of course, just as a side remark, I tried with 2 data scientists shortly after this. Why not try to learn machine learning the BSD conjecture to see how much you predict? And there we weren't doing so well. However, if you have a better data representation, you might be able to do well. So let me just, as a sort of a final example, let's take something from arithmetic geometry rather than hard prime properties. So very quickly, so if you take an elliptic curve, you have its local zeta function of such a form. Right? And then the point is that the L function, which is the coefficient, which is the numerator of the local zeta function, is governed essentially by a single integer. So this is the Euler coefficient of the L function of an elliptic curve. It has some properties which counts the number of points over Fp. But as far as we're concerned, luckily, there's this data is on LFMDB. So there's 3.5 million elliptic curves for which over the past 30 years, hardcore arithmetic geometers have computed these AP coefficients, right? This particular coefficient, the non-trivial one in the L function. But well, you take exactly the same trick. You define an integer vector of such a form. Take, I don't know, take the first 500 primes. So this is a 500-dimensional vector. And then you want to predict correct or interesting properties of elliptic curves just by looking at this. Well, as far as the BSD is concerned, so the hard so there's the weak and the strong BSD. The strong BSD says if you take the analytic properties of the L function, namely the order of vanishing, the Lth derivative L evaluated at 1, you should be this very sophisticated combination of various factors, most of which I don't understand. But hey, you know, whatever, they've been computed in this database. So there are 3.5 million cases of 500 vectors map into any one of these. So there are simple things like the rank of the elliptic curve, which is what at least I can understand. And then there are more sophisticated things like, you know, the Tamagawa numbers or the Shafirevich group. And then you just do this exactly the same experiment. So surprisingly, you can predict just by looking at these coefficients whether the rank of the elliptic curve is 0 or 1. So that's great. Even with a simple logistic regressor, you can tell to very high accuracy. And that's so. This we would have conjectured this, but unfortunately, this was already conjectured by Goldfield, Katz, and Sarnak. Is that rank 0 and rank 1 elliptic curves are at 50% each. So had they not conjectured this, we would have, and then this would be a very interesting test case for machine learning in terms of conjecture formulation. Another more sophisticated thing is you can even tell the torsion order with a Bayes classifier up to this level of accuracy. So there's definitely something there that can be encoded in this definition. So the hardest part of the BSD, I was told, is to do this the Shafirevich group, and that one did receive the lowest performance of them all. So indeed, something that's inherently hard is inherently hard even for machine learning. But nevertheless, the other ones are so easily predictable that had there not been already conjectures, one would have definitely conjectured this. So we actually just put a paper out today. Well, I didn't have time to include this. This is with Ki-Hwan Lee and Tom Oliver. And we had a very beautiful title called Murmurations of Elliptic Curves, where we plotted these AP coefficients, but averaged over elliptic curves over conductor range. And if you plot this, it gives extremely interesting fluctuations in sort of cosine, almost cosine-like behavior. And that is new, and that is something that you can do some kind of principal component analysis, which does distinguish different ranks. And at least so far, we checked with many experts. That is something new in the arithmetic geometry literature. So at least this kind of approach has generated something new that's worthy to look at. So this is that's totally cool. We're not just getting we're not just being assured by 99% accuracy performances, but there's actually a new pattern that has been sifted by looking at this kind of experiments. So I'm coming out to the end. So let me just conclude. Well, obviously this is great fun for mathematics and for physics, but on another level, this is kind of a suggestion. So here's a big red arrow if you try a generic machine learning algorithm to different branches of mathematics, I would say that there is sort of a hierarchy that's inherent to different levels of how hard is it for a machine to learn the structure of mathematics. So numerical analysis is probably the easiest. Somehow, surprisingly, algebraic geometry over C and arithmetic geometry are also very good. And then it gets harder and harder as you approach analytic number theory. So luckily, problems in string theory stay within the easy part of easy machine learnable part of mathematics. So this is, at least for physicists, we're very excited about this because, it gives a shot, forget about trying to study 10 to the 500 different algebraic varieties for string theory, it gives us a hope that you can actually find patterns in sifting universes. But it also gives a very peculiar glimpse of the entire landscape of mathematics, of how many problems in mathematics are well behaved under this kind of paradigm. So I won't bore you with all of this, but even over the past 2 to 3 years, there have been various experiments in different fields. So here's a paper in chemistry. There are papers in theoretical physics, and more recently, just last month, there's been this paper by Davies and all in Nature on how to use machine learning, exactly the same kind of ideas, on how to use machine learning to guide human intuition in terms of extrapolating ideas from mathematical data. So hopefully one day we're going to just feed into Sophia, which came into existence in 2017, which coincided with all this. In 2017, by the way, this is a robot that was given a human passport. So she's considered a citizen in Saudi Arabia with human legal rights. So hopefully, 30 years down the road, we'll give the likes of Sophia, here's a theorem, how would you go prove it? And then Sophia will go about gathering enough data, formulate a conjecture, or at least conjectural steps, and in conjunction with the ATP program, give you the intermediate steps of the proof. And then, while we just sit, we go have a cup of coffee, this will all be done within an hour, and then she'll LaTeX it for you and submit it to the archive. At least this is, let's hope, within the next 50 years. So with this very either frightening or exciting prospect, I'll end here. So thank you very much.
Thank you. I have a question. Will we be able to understand the proofs? Will they be too big for us to understand them? This is what I feel, right?
This is a very, very good question, and I think what is really interesting is I think what people like Buzzard are doing now. What he's doing, he's taking the space of proofs and then machine learning those to pick out the ones which are interpretable by humans. Syntactically, I think he's actually doing that. I've been thinking about doing something like this as well. And then, because so far, the proof of Pythagoras from like Euclid's axioms is very long, and it's not very humanly comprehensible. But I think with machine learning, by contextual analysis of all the papers in mathematics, we'll start to streamline over this and pick out the ones that are more, humanly understandable. And I think we'll converge towards the ones which are optimized towards human understanding. I think this is also on the way, almost in a scary way.
Yes. Do we have any other questions for the speaker? Please just speak.
Can I ask a question, which is actually a continuation of the previous question, but formulated differently? Where is fun? Normally proving theorem is fun. Where is fun?
Oh, for me, the fun is very much there because I'm not working on the ATP side of things. So for me, it's the fun comes in. Here's a neural network which is spotting this pattern. I can raise a conjecture and then let me try to prove that conjecture. So that's kind of fun. This is more of an experimental. This is for me at least, the top-down approach is more fun than the bottom-up, because the bottom-up is really very, very much into computer science approach. But the top-down is much more fun. It's like the fun comes. Just like what as I say, what the neural network is potentially doing is to spot x over log x. The fun comes in trying to prove x over log, at least guided in part by where I should approach this problem. So that still is very much fun.
I see. So it is more like experimental science.
Yes. Which things like this.
Yes,
so for example, this thing with Mignon. why should there be? The support vector machine has told me there's a separating hypersurface between simple and non-simple groups. Why should it be the case? Let's try to say, well, let me try to reformulate some statements in representation theory to try to prove that there does exist such a hypersurface. And that's the fun, for at least for fun-seeking mathematicians.
Good. Are there any other questions for Yang Hui?
Well, I'll ask another if nobody else will.
Yeah, of course.
I'm still stuck on the predicting prime, not prime, and I'm just kind of thinking through it a little bit. You removed the evens, for example, on your sequence, you said.
Yes.
If you included them, did your performance degrade? Likewise, if you said something was a prime that wasn't prime, what was its smallest factor? You see what I'm saying?
Yeah, these are good. I don't think I did this. I don't think I put in the even ones. These are good suggestions. But I mean, the code. It's very simple to code this up. I was just doing this. I wasn't even doing this on TensorFlow. I was just doing this on Mathematica because it's high level and I can get the prime information very quickly. And it's like 10 lines of code in Mathematica to generate this data. And that's a good suggestion. And you think maybe some kind is picking out multiplicity or something, multiples or something.
It might be interesting to see how it fails and how often it fails based on things. Likewise, you decide to sieve over just the odd numbers, removing the evens, but you might decide to remove all the multiples of the first n primes and see how the performance changes based on that.
Good point. Yeah, a very good point. To be tried. I thank you for these suggestions. These are definitely. I mean, it's such a simple problem, and if neural. See, one thing is I'm beginning to prefer support vector machines over neural networks because support vector machines are interpretable regarding Alethea's point. Because neural networks, there's so many parameters and so many things talking to each other. It's very hard to untangle it. But support vector machines are very good because you're plotting the data in some space and it's finding some separating hyperplane or hypersurface. So you can try a support vector machine on this prime problem as well. And I think I did try that, and it's given this kind of behavior. But it will be very, just do this binary vector to binary classification, and then just see how well the support vector machine is separating primes from non-primes, and that would be a good point. And the next time I will keep the confusion table so we can see how it's misclassifying.
Thank you very much. This has been fascinating.
Thank you for your suggestion. No, it's very simple to do this support vector machine on Mathematica. I highly recommend doing this on Mathematica. I converted from Mathematica to TensorFlow because I should be serious about this, and self-respecting data scientists should use TensorFlow. But then Mathematica since Mathematica 12, they've gotten so much better. Every year they come up with a new version. And in the last 5 years or almost every year, and then the neural network package and machine learning package in those are really high level and very efficient now in terms of performance. So I encourage everybody to just try this experiment, especially with the primes, because it's such a fundamental thing. And apparently, I think Sonax will give you some money if you can find even the slightest pattern in the Liouville lambda function.
It's quite hopeless, right?
Well, we think it's hopeless, but it's a cheap thing to do because it's like 10 lines of code. It's like it doesn't cost you. You just run on a computer, then you run away, have coffee, or think about your other problem while your computer is trying to search for some algorithm. And then if you find anything in it, it will be very interesting.
Okay, so I think we can thank our speaker again and for this great talk.
Thank you very much for having me.
Thank you. Thank you very much.